Hey guys, in this video we're going to talk about Chapter 9, Section 3 in the textbook, Convergence of Series. So last time we only looked at geometric series and whether or not certain geometric series converged or diverged. In this video we're going to look at other types of series and examine their convergence, not necessarily geometric series. So let's get started. First thing I want to do is kind of do a little review on the last video. We talked about geometric series. They have a common ratio, which we called x, and they also have a first term, which we called a. And it's really easy to check to see if a geometric series is convergent. All you have to do is see if that common ratio, if the absolute value of that common ratio is less than 1. If that's true, then it is convergent, and the sum is going to be the first term divided by 1 minus the common ratio, and divergent otherwise. So let's do a quick example to remind ourselves what these series looked like. So it says determine whether the series is convergent or divergent, and if it's divergent, go ahead and find the sum. So right off the bat, we can notice that this thing is indeed geometric, because from one term to the next, I have to multiply by a certain number. And what is that number? Well, that number is going to be negative 2/3, right? So to get from 5 to negative 10/3, we better multiply by negative 2/3. To get from negative 10/3 to 20/9, we better multiply by negative 2/3, and so forth. So that's our common ratio. That's x. X is going to be negative 2/3. This is our common ratio. And it turns out that the absolute value of negative 2/3 is equal to 2/3, and that's less than 1. So that tells us that this series is convergent. Oops, sorry. And what does it converge to? Well, it converges to the first term divided by 1 minus x. So our first term is 5. This is a. So a is 5. X is going to be negative 2/3. And so the sum, by our formula above, is going to be 5 over 1 minus negative 2/3, which is 5 over 1 plus 2/3, which is 5 over 3/3 plus 2/3 is 5/3. So that's going to give us an answer of 3. So this is the sum. And so that's a little review from last week. Now let's look at some examples of series that are non-geometric. So one way to do this, to determine whether a non-geometric series converges or diverges, is we look at the behavior of the partial sums. And in general, this isn't always going to work, and you should sometimes avoid this if you can do easier things, but I just want to show you guys, how this works. So first of all, we have this series, so we have this series with a sub n is 1 over n times n plus 1. So we could write it like this. We could say that we're starting at n equals 1, we're summing up to infinity, and the thing that we're summing is going to be 1 over n times n plus 1. Okay, so remember how we notated this. We start at n equals 1. And so what I can do is I can actually expand this. I can just write it as 1 over 1. It's 1 plus 1. So this is when n equals 1. We go up to n equals 2. And we have 1 over 2 times 2 plus 1. Go up to n equals 3. 1 over 3 times 3 plus 1, etc. And simplifying this out even more, we get 1/2 plus 1/6 plus, let's see, what is this going to be? 1/12. Let's do one more. This is going to be, the next one is 1 over 4 times 4 plus 1. So this last one's going to be 1/20, and then ... Okay, so that's what our series looks like. Now that we have an idea of what it looks like, we can see that this thing's not, first of all, we always want to check first first thing you want to check, is it geometric? If it's geometric, it's very easy to tell whether it's convergent or divergent. We just simply look at the absolute value of the common ratio, just like we did last week. But we can see that this isn't geometric. For instance, if we look from the first term to the second, what do I have to multiply 1/2 by to get 1/6? I have to multiply by a third. Now, what do I have to multiply a 6 by to get a 12th? Well, I have to multiply by a half. Now, since these two ratios are not the same, we can automatically conclude that this thing is not geometric. So we need another way to deal with this. Geometric is always I think it's one of the easiest series to work with. But this is not geometric. So, what can we do? Well, what I can do is I can look at the partial sums and look at what happens when the partial sums tend to infinity. So remember what the partial sums were. Well, the first partial sum is just literally the first sum in our series, 1/2, right? The second partial sum was going to be the first two terms added together in our series. Okay, so when we do that, that's going to give us 2/3. The third partial sum, again, I'm just adding up the first three terms in my series. So the nth partial sum is going to be the first n terms in your series. So we have this plus 1/12, and that's going to turn out to be 3/4. So what we can see here is that we have a pattern emerging, and hopefully you guys can see what that pattern is. So let's see what this is going to give us. This is going to give us 4/5. So how can we write the nth partial sum in terms of n? What do you notice about the relationship between n and the nth partial sum? Do you see any relationship here? So maybe I'll write this down. What do you notice about the nth partial, or maybe how about this? What do you notice about S sub n, the nth partial sum? Well, we can write the nth partial sum in terms of n, it looks like, right? And this pattern is going to continue forever because we have a formula, and it's and there's really not going to be any deviation there. So what we can say is that S sub n is going to be n over n plus 1, right? For this first example, n is 1, right? This is our n is the subscript. And so this matches up with our formula. This is 1 over 1 plus 1, which is 1 over 2. This n is 2, so this is n equals 2. And our formula agrees with this. This is going to be 2, so n over n plus 1 is 2 over 3. You see that? So now we have a formula for the nth partial sum, and what happens as n goes to infinity? In other words, what happens if we sum up infinitely many terms in our series? Well, let's see. So if we take the limit as n goes to infinity of S sub n, this is going to be the limit as n goes to infinity of n over n plus 1. Now, do you guys remember how we dealt with this in calculus? We can do two things. If we really wanted to, we could do L'Hopital's rule. Another strategy that we used last semester is we divided top and bottom by the highest power term. Okay, so the highest power term here is n, right? If this was n squared over n plus 1, the highest power term would be n squared. Okay, so let's go ahead and divide top and bottom by n. So we have n over n plus 1 over n. And this trick is valid because when we divide top and bottom by n, we're essentially just multiplying by 1, right? When I divide top and bottom by n, I'm essentially multiplying by 1. So simplifying this down, we get the limit as n goes to infinity. N over n is just 1. Again, over 1 plus 1 over n. And if I plug in infinity in for n to see what's going on here, well, remember, this guy goes to 0, right? If I have 1 over something enormous, that's going to the number 0. So this is 1 over 1 plus 0, and that's simply 1. So that's our answer here. This converges to 1. And we figured that out by looking at the partial sums. Okay, so the next example that we're going to look at is a very famous series in mathematics called the harmonic series. And that series is 1 over n, starting from n equals 1 to infinity. And so basically this is what this looks like. You know, all of our terms added up, 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, etc. And we want to show that this harmonic series is divergent, which may not be obvious at first, but it has a really cool and beautiful proof that I want to try to hash out for you guys. So the way that it works is, well, this is the way that I'm going to set this up. What we're going to do is we're going to look at the partial sums of the form s sub 2 raised to the n. And notice a pattern. Okay, so that's what we're going to do. So the first, when n equals 1, so s sub 2 to the 1, if we just plug in 1 first, this is just simply going to give us s sub 2. And what this means is just, hey, add up the first two terms in this series. So this is 1 plus a half. Okay, so it's 1 plus a half. Let's look at the next one. So this is s sub 2 squared, which is s sub 4. And so that just means, hey, add up the first 4 terms in the series. 1 plus a half plus a third plus a fourth. And what I want you to notice here, this is the trick. We're going to look at these guys right here. 1/3 plus a fourth. And notice that this sum is going to be greater than 1/2. Well, why is that? If you imagine for a second that 1/3 is 1/4, right? 1/4 plus a fourth is a half. Okay, forget the 1/3. 1/4 plus a fourth is a half. But we know that 1/3 is larger than 1/4. So this sum had better be larger than a half, right? So that's the argument that we're going to use here. Okay, so that's going to be bigger than a half, and therefore s sub 4, let's maybe write it down here, therefore s sub 4 is going to be greater than 1 plus a half, and then this yellow part becomes plus a half, right? Because this sum was greater than a half. Okay, so that's that. And 1/2 plus a half is just 2 halves, and I'm going to write it like that, and you'll see why in a second, but let's change 1/2 plus 1/2 to 2 halves. just so we can see what the pattern is. Okay, so far we've established this. Now let's look at for the next n, when we increase to n equals 3, this becomes s sub 2 to the 3, which is s sub 8. And we're going to use the same argument here. So what we have is the first 8 terms added up. This is really just, I don't know, this is mind-blowing to me. Hopefully you guys can appreciate this. There's also lots of videos on this. I know that Khan Academy has another video of the divergence of the harmonic series. I don't know if he uses the same proof as this one, but this is a pretty classic proof. Okay, so here's the first 8. Now, what do we know here? Well, we know that from above, this was greater than a half. And we can use a similar argument to the one above to say that, hey, guess what? This is greater than a half. Why is that? Let's talk through it. Well, again, imagine all of these terms that don't have a denominator of 8 were 1/8. So imagine this was 1/8 plus 1/8 plus 1/8, and then the last 1/8, of course, plus 1/8. Well, that's 4/8, which is a half. Now, okay, so that's the big picture. Looking at the individual terms, 1/5, 1/6, 1/7, those are all numbers larger than an eighth, right? So if that's the case, then this whole sum had better be bigger than a half. This is giving me chills. Not really, but it is super cool. I hope you guys can appreciate this. All right, so that's greater than a half. Now, let's go up to the next n equals 4. So we have s2 sub 4. This is simply s sub 16. Okay, so that's the first 16 terms. And I'm going to write this out just because I want to be thorough, but you don't have to. If you don't want to, you can use some dots, but I'm going to just make sure we're super thorough here. Actually, here's what I'm going to do. I'm going to just leave that. And then maybe we'll do it like this. Okay. All right, so above we established that, well, actually, I should probably write something on the previous line. This whole thing is going to be, so s sub 8 is going to be greater than 1 plus, well, we have a half plus a half plus a half. So this is telling us that s sub 8 is going to be greater than 1 plus 3 halves. All right, let's keep that on the back burner. Okay. All right, so let's use what we already established, that this guy right here is going to be greater than a half. This guy right here is also going to be greater than a half, and I think you guys know what's coming up next. This guy right here, how many terms do we have? 1, 2, 3, 4, 5, 6, 7, 8 terms. Now, again, this is going to be greater than a half by the same logic, right? Because all of these numbers right here, if these were all 8 over 16, or, well, actually, let's put it a different way. What would all of these numbers have to be to add up to 1/2? Well, 1/2 is 8 over 16, right? So all of these would have to be 1 over 16. Right? All of these would have to be 1 over 16. There's 8 of them, so these would all have to add up to, if they were all 1 over 16, they would all add up to 8 over 16, which is 1/2. But we can see from the denominators that, 1 over 9, 1 over 10, 1 over 11, all the way to 1 over 15, these numbers are all larger than 1 over 16. So this sum had better be bigger than 1/2, right? And we can keep using the same argument here. Let me erase some of this. So this sum is going to be greater than 1/2, and therefore S sub 16 is going to be greater than 1 plus 1/2. That's this first part. Plus 1/2, plus 1/2, plus 1/2. And condensing this, we have S sub 16 is greater than 1 plus, how many halves do we have? 4 halves. All right, so hopefully you guys are seeing the pattern here, right? S sub 16, S sub 4. So in general, what can we say about S sub 2 to the n? Well, what we can say, and it's clear from this pattern here, another thing you can check is that S sub 32 is greater than 1 plus 5 over 2, and S sub 64 is greater than 1 plus 6 over 2, etc. Well, we can say that, we can say that as n goes to infinity, S sub 2 to the n is greater than 1 plus n over 2, right? Just looking at the pattern here. Again, this guy was n equals 2. This was n equals 3, n equals 4, and so forth. So what does this tell us? Well, this tells us that the sequence of partial sums, S sub 2 to the n, is going to go to infinity, right? And, right, because as n gets really huge, this whole thing goes to infinity, and what can be bigger than infinity? Well, nothing, right? So this thing has to go to infinity as well. And so what we can conclude here is therefore 1 over n from n equals 1 to infinity, this series diverges. Now, I'm not going to ask you to prove this, but you should hang on to this in your back pocket, that this series diverges, because we are going to be using it to prove other things. So just keep that in mind. 1 over n diverges, that series does. And let's go ahead and move on here. Okay, so I'm going to give you some properties of series, some convergence properties. You should just copy these down for now. I'm going to go into depth into each one. I'm not going to prove each one. I'm going to prove number 3, but I really want you guys to just have these in your notes so that you can use them. Yeah, okay, so let's go ahead and scroll down. And we're going to talk about these in just a moment. Okay, so there's 4 different properties that you're going to have to know. Okay, so let's look at example 1. So this is property 1 from what I just showed you guys. Okay, this is a utilization of property 1. So we're trying to find the sum of the infinite series 3 over n times n plus 1 plus 1 over 2 to the n. And the way that we can do this is we can break this up. Well, first of all, we want to notice that both of these guys are going to converge. And how do I know this? Well, this is from the previous example. The previous example, let's go back to it actually. This guy, we prove that this guy converged to 1. 1 over n times n plus 1. So if that converges to 1, so since 1 over n times n plus 1 converges to 1, then by property 1, so this is the second part of property 1 that says that k times a to the n converges to k on the outside times the sum. Converges to 3, right? K is equal to 3 in this case. Okay, so that converges definitely. This guy converges because it's geometric, right? We have, when n equals 1, we have 1 over 2. When n equals 2, we have 1 over 4, etc., etc. So we can see that the common ratio here is 1/2, and the first term is also 1/2. So our sum is going to be first term over 1 minus common ratio, and that's going to give us 1/2 over 1/2, which is 1. So we have a convergence to 3 and a convergence to 1, and by property 1, right, in the previous slide, we can, since they both converge, we can simply take the sum of what their limits are, right? So let's write this out. Okay, and we just said that the first one was 3, right? And then the second one was 1. So this is coming from first one and the second one. So this is going to give us a net result of 4. So this is our sum of the series 3 over n times n plus 1 plus 1 over 2 to the n. Okay, so this is going to be an example of, so this is an example of property 2. Now, what does property 2 say? Property 2 says that basically, if we add or subtract a finite amount of terms to a series, it doesn't change whether it converges or not. However, it may change the sum. Okay, so that's a pretty important concept here. Let's go ahead and look at this with an example. It says investigate the convergence of this guy and this guy. Well, I'll first look at we're going to look at the first one. We're going from n equals 1 to infinity, 5 is 1/2 to the n. And if I expand this out just to see whether or not it's geometric, we have 5 times 1/2 to the first, plus 5 times 1/2 to the second, plus 5 times 1/2 to the third, and so forth. So what we can see here is our common ratio is going to be 1/2, right? This is indeed geometric because we're multiplying each successive term by 1/2 to get the next one. And our first term is going to be 5 times 1/2, which is just 5/2. So what this tells us is that our sum, well, first of all, this guy, the absolute value of this guy is less than 1, so right off the bat we know it's convergent. That's what we know about geometric series. And so the sum is going to be the first term over 1 minus the common ratio. So I have 5/2, 1 minus 1/2 is 1/2. So that's just going to give us 5. Okay. Now let's look at this other one. So here, the only difference is that instead of starting at 1, we're starting at 3, which basically, like, the difference between n equals 1 and n equals 3 is finite, right? There's only 2 terms in between. So the sum may be different, but it's not going to affect the convergence, is what property 2 is telling us. So let's look at this. So we're going from n equals 3 to infinity of 5 times 1/2 to the n. And we can expand this. This time we're starting at 3. So we have 5 times 1/2 to the third, plus 5 times 1/2 to the fourth, etc., etc. Okay. And we can see, again, the common ratio is still 1/2, really, because we really just shifted this series over, if you want to think about it like that. But this time, our a is different because a is our first term. In the previous example, the very first term was 5/2. In this case, it's going to be 5 times 1/8, which is 5/8. Now, again, this ratio right here is the same. We simply shifted to another spot in the series, and because of this, of course, it's still going to be convergent. However, the sum is going to be different. Now, the sum this time, if we start with our initial term, we have 5/8 instead of 5/2. And we're still going to be dividing by the same thing, which is 1 minus 1/2. So this is 5/8 over 1/2. So we end up getting 5/4. So basically, going from here to here, we're adding finitely many number of terms here. So if we add or subtract finitely many terms, it's not going to affect the convergence in any sort of way. However, as we can see, it did affect the sum. Okay, so the third convergence property of series is going to be the following. If the limit as n goes to infinity of a sub n is not equal to 0, or that limit doesn't exist, then the sum diverges. Note that you cannot conclude that it is convergent if it equals 0. The only thing that you can do is, if you get a number that's not equal to 0, you can definitely say that it diverges. But if it's 0, you can't say either way if it's convergent. So let's go ahead and do some examples with this. So this is an example of property 3. And I know I said I was going to prove this earlier in the video, property 3, but I think I'm going to wait until a later video to do that just for time's sake. Okay, so we want to show that this series right here diverges. And what property 3 is saying is that I want to look at the limit of a sub n, which is this right here that I circled. I want to look at the limit as n goes to infinity of n squared over 5n squared plus 4. Now I can use the trick that I did in a previous example. I divide top and bottom by the highest power term, and that's n squared. So if I divide the top by n squared, I get that over 5n squared over n squared plus 4 over n squared. Simplifying this out, I get 1 on top. On bottom, n squared over n squared is going to cancel. And I get this. So here's my little trick. I can plug in infinity at this point for n. And I get 4 over infinity squared. Well, that's just infinity, right? So this is 1 over 5 plus 4 over infinity. And this, of course, goes to 0. So I'm left with 1 over 5 plus 0, or 1 over 5. Now, property 3 says this number is not equal to 0, and therefore the series diverges. Okay, so since that number is not equal to 0, it's going to diverge. So that's one little, one other trick that you can use to see whether or not it diverges, a series diverges. Let's look at another example. So this is going to be an example of property 4. Let's go back. So this was property 3. Property 4 is this guy. So basically, if you have a series that diverges, if you multiply a constant multiple by that argument a sub n, that's also going to diverge. Okay, so how can we use that for this problem? Well, notice that in this case, so this is property 4 example. Notice that in this case, our k is equal to 3, right? We can rewrite this as n equals 1. Bring the 3 out in front of 1 over n, right? Now we know this is the harmonic series. So we know that this diverges, and you can use that in your homework arguments too. Like if you run into the harmonic series, you can say, we know it diverges. You don't have to do the proof over again. So since that diverges, that means that this also has to diverge. By property 4. All right, so that is that. Let's see what's next on the agenda. All right, so now we're just determining whether this series is convergent or divergent. If it's convergent, find its sum. So what I like to do first is I always want to check to see if it's geometric. And that's always the easiest way out, I think, usually. So let's see. Is this geometric? Well, a third times what is a 6? That's a half. A 6 times what is a ninth? Well, who knows, but not a half, right? Okay, so this is not geometric. So, not geometric. And we move on to the list. we move on to the next thing in the list. Now, what I can do here is I can actually write this as an explicit sum instead of just writing it expanded like that. So I can actually write this, if you notice, we're going from 3 to 6, 6 to 9. These are all multiples of 3, right? This is n equals 1, n equals 2, n equals 3. And so we can write a formula for this. We can say that this formula, we're adding up all the numbers starting at n equals 1 to infinity, and the formula is 1 over 3n, right? That's our formula. Plug in n equals 3, we get 1 over 9. Plug in n equals 5, we get 1 over 15, etc. So that's our formula. And right off the bat, we notice something, right? This looks very suspiciously like the harmonic series 1 over n. So this can actually be written, if I pull the 1 over 3 out in the front, I have n equals 1, 1 over n. So that can be written like that. And this thing diverges, right? This harmonic series diverges, and therefore 1 over 3, so k, 1 over 3 is just a constant. Therefore, this whole thing diverges. And how did I know this? This is by property 4. This is by property 4. This is just k times a series that we know diverges. So the whole thing has to diverge. Okay, let's do another example. So let's see. Okay. Determine whether, again, we want to see if it's convergent or divergent. And we're already given an explicit formula, which is nice. Is it geometric? That should always be your first question. Well, if I expand this thing out, when n equals 1, I get this. When n equals 2, I get this. When n equals 3, I get this. And etc. Well, maybe we'll do one more. When n equals 4, we get this. So simplifying these out, the first one, 1 minus 1, is clearly 0, over, and then the second one is 1 over 5, then I have 2 over 8, and then I have 3 over 11. So this is, this is not geometric, right? 0 times what is a fifth? That's 0. 1/5 times 0 is definitely not 2/8. So this is not geometric. All right, so we need to go to plan B. So plan B is to use the 4 properties. And the first property, if you look at it, we have sums, right? We don't have a sum here, so we can pretty much get rid of that. The next property that you should try is you should probably look at the third property. So look at property 3 if the geometric series doesn't work. And we don't have a sum. So if the geometric series doesn't work and we don't have a sum, let's try property 3, which is to take the limit as n goes to infinity of this explicit formula. So let's do that. So we're taking the limit as n goes to infinity of n minus 1 over 3n minus 1. And again, I'm going to use my sneaky little trick. I'm going to divide top and bottom by the highest power, which in this case is n. So we have n over n minus 1 over n all over 3n over n minus 1 over n. Cleaning this up, we have n over n is 1 minus 1 over n. 3n over n is just 3 minus 1 over n. And at this point, we can plug in infinity for n. So we get 1 minus 1 over infinity over 3 minus 1 over infinity. Now both of these goes to 0, right? And so this is just equal to 1 over 3, which property 3 says, hey, if this number is not equal to 0, this thing's divergent, right? So 1/3 is not equal to 0, and so therefore by property 3, the sum is divergent. And I'm being a little lazy with the indices here, but that's the idea. Okay, so try to see if it's geometric first. If it's not geometric, see if it's a sum of two series. If it's not a sum, then look at property 3, which is this looking to see if this rule approaches 0 when n goes to infinity. Okay, so let's go ahead and look at this one. Now I can break this up into a sum. Okay, so this is we're probably going to use property 1 here, right? Because what I'm noticing is that I can chop this thing up. I can break this into 1 over 3 to the n plus 2 to the n over 3 to the n, right? Right off the bat, I can see that. So, and maybe I should be less lazy and just put the bounds up here. Let's do that. Now, both of these are geometric, right? So, if they both converge to some number, then I can just add the two numbers up. One for this one and one for whatever this converges to. I can just add them up. Now, do these converge? Okay, so this is geometric. And that's because if we expand this out, 1 over 3 to the first plus 1 over 3 to the second plus 1 over 3 to the third, and so forth. So the common ratio here we can see is 1/3. And this, the absolute value of 1/3 is less than 1, so this is convergent. That's a good sign. Our first term in this series is 1/3. That's this guy. So, the sum is going to be our first term over 1 minus our common ratio. So this is going to give us 1/3 over 2/3. And that is simply going to give us, let's see. That is going to give us, that's going to give us a half. Sorry, that took way too long to do that. So that's my sum for the first one. Let's make this red, actually. Now for the second one, this is also geometric. Let's see why. Plugging in n equals 1, I have 2 to the first over 3 to the first, plus plugging in n equals 2 to the second over 3 to the second, plus 2 to the third over 3 to the third, plus dot, dot, dot. So we can see here that our common ratio is 2 over 3. I have to multiply each successive term by 2 over 3 to get to the next one, right? So that's geometric. So our common ratio is going to be 2/3, and also our initial value is 2/3. Now, since 2/3, the absolute value of that is less than 1, this is convergent. And so what property 1 tells me is since both of these guys are convergent, both the red and the green sum, since these are both convergent, we can simply take the sums of each of these and add them together. So we found the sum of that guy, and the sum of this guy we can find in a similar way by using our formula for convergent geometric series. So the sum is just going to be 2/3 over 1 minus the common ratio. And it's going to give me 2/3 over 1/3, which is just going to give me 2. So that's the sum there. And so my answer, my total sum, again, this is by property 1, is just 1/2 plus 2, which is 5/2. So that is the sum of our original series right up here. And that was, we used property 1 to get there. All right, let's look at this. We want to determine whether the series is convergent or divergent. Okay, so how are we going to deal with this? Well, I don't really like radicals when I'm trying to look at sums of series. So I'm going to rewrite this instead of to the nth root. I'm going to rewrite this as the sum going from n equals 1. Oops, let me do that again. So we're going from n equals 1 to infinity. And instead of the nth root of 2, I'm going to rewrite this as 2 to the 1 over n. These two things mean the same exact thing. Okay, so since that's the case, I can't use property 1. We don't have a sum. This isn't geometric. You should prove that to yourself, that this is not geometric. So we need to take another tactic. So what I'm going to look at is property 3. We're going to look at property 3. And we're going to take the, and property 3 says, hey, take the limit of this guy as n goes to infinity. And if it doesn't equal 0, then this thing is divergent right off the bat. So let's check this out. So we're taking the limit as n goes to infinity of 2 over 1 to the n. Now, if I plug in infinity for n, this is going to be limit as n goes to, well, actually, let's just write it like this. This is going to be 2 raised to the 1 over infinity. Well, what is this going to go to? That's going to go to 0. So that means this thing is going to go to 2 to the 0, which goes to 1. So by property 3, since what we got here when we took the limit as n goes to infinity, since 1 is not equal to 0, the series that we had, the original series that we had, this thing diverges. This does not have a sum. Okay, so that is my answer there. Okay, let's take a look at this guy. All right, so yeah, we have a sum, but it's not really a sum that we can separate into two separate series. Property 1, probably not going to be too useful here. What else could we look at? Well, it's not geometric either. You should check that. It's not geometric. There's no common ratio here. However, we can look at property 3 again. So we're going to look at property 3 because it's not geometric and we can't break this up into a sum of two things. So property 3 says, hey, I'm going to take the limit as n goes to infinity of this guy. So we're taking the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1. Okay, so again, I can do that trick of multiplying by 1 within the ln sign. That is, I'm going to divide top and bottom by the highest power term, which is n squared. So let's go ahead and do that inside the ln. So I have n squared over n squared plus 1 over n squared, all divided by 2n squared over n squared plus 1 over n squared. And let's just simplify this. So the limit as n goes to infinity of ln, well, this goes to 1. On bottom, this goes to 2 plus 1 over n squared. And at this point, if I plug in infinity here, I get the following. I get ln of 1 plus 1 over infinity squared over 2 plus 1 over infinity squared. And these guys both go to 0. And so what I'm left with is ln of 1/2, which is not equal to 0. And therefore, I do these 3 dots for therefore. Therefore, by property 3, this series diverges. Okay, so the next thing we're going to look at is theorem 9.3, which is the integral test. Basically, we're going to be looking at series and corresponding functions for said series. We're going to be looking at comparing the integral of that function to the actual infinite series. And you have to have some criteria to do this. It's very important that the function that you're integrating, that you're looking at the series of, is positive and decreasing. If these two things aren't true, then forget the integral test. Use some other tool to determine convergence or divergence. However, if it is positive and decreasing, you can use this test. And so basically what we're going to be doing is we're going to be looking at the integral of f of x from 1 to infinity. If it converges, then the infinite sum of that function also converges. And if it diverges, then the infinite sum diverges. And we're going to look at why this is true, get some intuition behind, why this is true. Also, a corollary here is that the p series, the infinite series of 1 over n to the p for power p is greater than 1 converges, and it diverges if that power is less than or equal to 1. So another useful bit of information to keep in your back pocket. Okay, so using the integral test, show that the harmonic series diverges. We already showed that it diverged with that really interesting proof before. But let's go ahead and do this another way. So what I'm going to be looking at is I'm going to be trying to compare. I'm going to be comparing the harmonic series, this guy, which is equals 1. I want to compare this to the integral 1 to infinity of 1 over x dx. Right? I want to compare these two quantities. So the first thing is I'm gonna look at a graph here and actually first verify, is this 1 over x, or maybe we can just say is our function f of x equals 1 over x positive and decreasing. Is that true? Well, yeah. Each of these terms is positive, and they're constantly decreasing as we march along. So yes, this is true. We can definitely use the integral test here. So what we're going to do, just to give you some intuition of what's going on, is I'm going to draw the graph of 1 over x. And so let's see. So here's 1, and here's my x-axis right here. This is my y-axis, or f of x. And I can go from 1, 2, 3, and 4. And so if I plot this graph right here, 1 over x, when x is equal to 1, our output is 1. When x equals 2, our output is a half, and so forth. You guys know how this goes. Okay, so we have this function right here. So this is f of x equals 1 over x. Now, so we want to compare this to the infinite series, right? N equals 1 to infinity of 1 over n. And if I expand this out, this is just 1 plus a half, plus a third, plus a fourth, and so forth, right? How can I incorporate this into the picture that I have drawn? Well, we can think of each of these guys, each of these terms in the sum, as a rectangle with width 1 and height f of n, right? So for example, I can look at this rectangle right here. The area of this rectangle right here, well, the area is going to have a width of 1 and a height of f of 1, right, which is 1. Okay, so that's representing this first term here. Then we can add on to it the next rectangle, the area of the next rectangle. Well, again, I still have a width of 1, but this time the height is f of 2, which is 1 over 2. And so forth. So here we have this guy. This is the area. So the series represents the area of all of these rectangles, all the way off to n equals infinity. And we can see that that area is definitely larger than the area represented by the integral, right? Because the integral, by definition, is just going to be the area under the curve, right? And so maybe I should write this out. So what we can see from the picture is that the area that the series, which is the orange rectangles, right? The area that the series represents is larger than the area represented by the integral. We can see that. The area represented by the integral is that yellow area under the curve, whereas the area represented by the series is the area of each of these rectangles, which includes all of the area under the curve plus some more up top, which you can see here. So all that excess is in red. And therefore, what we can say, if the integral, I'm being sloppy here, but if this integral diverges, then the series must diverge as well. Right? And we can see that, right? Because if the area under the curve diverges, if we add on the excess, this red piece, well, that's going to have to diverge as well because it's larger than the area under the curve. So that's the idea here, okay? So we're going to show that this thing diverges. And if that diverges, then the series diverges because of the integral test. Okay? So what do we have? We're going from 1 to infinity of 1 over x dx. And we know what this is. The antiderivative of 1 over x is simply ln of the absolute value of x. So this goes to 0, but ln of infinity, this is going to be infinity, right? And so this is going to be divergent. And so when we integrate this, since this is divergent, then it follows that the series is also divergent. So that's another way to show that the harmonic series is divergent. All right, so 1 over n, the series of 1 over n from 1 to infinity diverges, but it might surprise you that 1 over n squared actually converges. How can we show this? Well, we're going to do a similar trick, but instead of using the overestimating rectangles, we're going to underestimate. Let me show you what I mean by that. So, first of all, to even use the integral test, we need to ask ourselves, is the corresponding function f of x equals 1 over x squared positive and decreasing? If the answer is yes, then we can proceed. If the answer is no, we have to use something else. Well, the answer here is yes, because if we plug in x equals 1, we get 1, x equals 2, 1 over 2 squared is 1 over 4, 1 over 3 squared is 1 over 9, and so forth. So yes, this is definitely, these are all positive, and the terms are decreasing. So that's good. So we can use the integral test. So what we want to do is want to compare our series that we were given to the corresponding integral. So we're going from 1 to infinity of 1 over x squared dx. Okay, so let's go ahead and draw a picture of this. Again, just like we did before. And I'll say this is 1. Maybe we have 1, 2, 3. So let's graph the curve 1 over x squared. 1 over x squared is going to look something like this. Just a rough sketch here. So that's 1 over x squared. And now the idea is to consider the series as an underestimate. So what do I mean by that? Well, what was our series again? Our series was 1 plus a fourth plus a ninth plus dot dot dot. And so what I can look at now is I can look at this rectangle. This represents the first term in my series 1. That's an area of 1. And then I can look at the second rectangle here. And the second rectangle is going to be this guy. Let me do it in red. So this guy represents an area of 1/4. So this represents the second term in my series because, again, the base is 1 and the height this time is 1 over 2 squared, right? I'm just plugging in 2 into my function to get 1/4. Okay? So now you can see that what we have here, you know, if we ignore this piece right here, under the curve is an underestimate, right? So let's look at the next one. Let's look at this one. So this guy is going to, this rectangle is going to represent the area of 1/9 because, again, this width is 1 and the height here is going to be f of 3, which is 1 over 3 squared, which is 1 over 9. Okay? So what can we say here? Well, we can say the following. We can say that if we can show that 1 over x squared, if this integral from 1 to infinity dx, if we can show that this converges, well, then we can also show that the series converges. Why is that? Because looking at the area under the curve, if the area under the curve converges, then the area that's less than under the curve is also going to converge, right? Because the area of the rectangles is less than the area of what's under the curve. And even if we add on this finite area right here, that's by property 2, this says if we add on that finite area, it's not going to affect the convergence at all, right? So that's the idea here, is that this integral is acting like an upper bound of the series. And it's saying, hey, if the area under that curve is finite, well then this underestimation, the area of the sum of these rectangles had better be finite as well. Okay. So this time, I'm kind of using this as an underestimate. So let's investigate this and see if it converges. If it does, hey, well, we are in business. Then the series converges. So let's compute this. So we're going from 1 to infinity, being a little bit sloppy here, but remember how we computed these infinite integrals? We took the limit as b went to infinity from 1 to b of 1 over x squared dx. And if I go ahead and compute this, 1 over x squared is the same thing as x to the negative 2. So if I add 1 to that power and divide by negative 1, I get negative 1 over x as that antiderivative. So this is going to be the limit as b goes to infinity of negative 1 over x from 1 to b. Okay, so let's plug in our values here. We get negative 1 over b minus negative 1 over 1. And what is this going to give us? Negative 1 over b plus 1. All right, so if we plug in infinity here, we get negative 1 over infinity plus 1. This goes to 0. And so this converges to 1. Now, that's not to say the sum of the series is 1, but this integral is 1. And so since the integral, or since the sum of the Riemann sum converges, then that series converges as well. It has to, since the integral is acting like an upper bound here. All right, so that's how we can use the integral comparison test. Let's do some other examples here. Okay, let's see what we got. Okay, all right, so it says use the integral test. I know it says in the directions, but let's check just to make sure that it's positive decreasing. Well, let's see. So when n equals 1, we have 1 over 2. When n equals 2, we have 1 over 5, and then we have 1 over 10, etc., etc. So yes, this is positive and decreasing. So we can use the integral comparison test. So we're going to look at the corresponding integral from 1 to infinity of 1 over x squared plus 1 dx. So we're comparing these two. If this, when we take the integral, if this converges, then that means this converges. If it diverges, that means that diverges. So let's go ahead and do this. Now, you'll notice that if you go back to your lovely integral table, 5-24 looks promising to use to find the antiderivative here. So let's go ahead and use that. Let me see my table. So yeah, basically what this says, actually, is it 5-24. So basically what it says is the integral of 1 over x squared plus a squared dx is equal to 1 over a tan inverse of x over a plus c. Now this is a definite integral, or we're going to be treating it like a definite integral, so we don't have to worry about the plus c. But anyway, you can see that a is 1, right? 1 squared in this equation. So when we apply this here, we get 1 over a, which is simply 1. Maybe I'll write it just to be thorough. Tan inverse of x over 1. And we're not doing plus c. We're evaluating from 1 to infinity. And so what we end up having is tan inverse of infinity over 1 minus tan inverse of 1 over 1 using the fundamental theorem of calculus. This we talked about before, but basically it's saying which angle has an output of infinity, and that's going to be pi over 2. Right? If you look at your unit circle, that's where tangent is undefined. So tan inverse of infinity is going to be pi over 2 minus tan inverse of 1. Well, tan inverse of 1 is pi over 4. That's where tangent is equal to 1. And when we do this computation, we get pi over 4. This is a number, and so this is convergent. This is convergent. Now this, again, I want to stress this. This is not the sum. This is not the sum of this necessarily. But when we do take that integral, it is going to tell us that that the series is convergent. So therefore, the original series, which was 1 over n squared plus 1, from 1 to infinity, is also convergent. But we're not saying anything about the sum quite yet. Okay? Let's do another example. So again, using the integral test, so I'm going to leave this as an exercise. Check first that this guy is positive decreasing. It is, but you should check that. So it's the only way that we can use the integral test if those two things are true. So assuming that they are true, let's go ahead and integrate its corresponding function here. So we're going to set the integral from 1 to infinity, and we have 1 over 2x plus 1 to the third dx. Okay, how do we integrate this? So go back into your memory from the end of Calculus 1, or when we did integration by parts. This is going to be a nice u substitution problem. So what I'm going to do is I'm going to let u equal 2x plus 1, and therefore du, taking the differential of both sides, du is equal to 2 dx. Dividing both sides by 2, I isolate dx, and I get dx is equal to du over 2. Okay? So putting that new information in here, I have 1 over u to the third, and dx we just said was du over 2. Right? Just doing those substitutions there. And I'm going to pull out a 1 over 2 just to make this look a little bit nicer. And the 1 over u to the 3, I'm going to write that as u to the negative 3. You guys know the drill. Now let's take the antiderivative. Adding 1 to that power, I get u to the negative 2 divided by negative 2, going from 1 to infinity, and that 1/2 is on the outside. Plugging u back in, 2x plus 1, I get 1/2 times 2x plus 1 to the negative 2. And actually, well, maybe we'll do that in a second. Let's go like that. Now I'm going to move that 2x plus 1 to the negative 2 to the denominator. Whenever you're working with infinities, that's a good thing to do. You know, because if the denominator is infinity and the numerator is a constant, you got 0. So that's where I'm at so far. And using the fundamental theorem here, I get okay. Now this thing, the bottom 2 times infinity plus 1 squared, that's infinity. Infinity squared is infinity times negative 2. That's just infinity, right? Or times 2 is infinity. So essentially I have negative 1 over infinity. Let's just write that out. And then over here, if I evaluate that thing, that is going to give me, let's see, 2 plus 1 is 3. Let's see, 3 squared is 9 times negative 2 is negative 18. So these become a positive. So that becomes a positive. And of course, we know that this is going to be 0. So this is going to be 1/2 times 0 plus 1 over 18, which is going to give us 1 over 36. It's a number. It's not infinity. So this tells us that the integral converges. And since that's the case, the corresponding series, which was 1 over 2n plus 1 to the third, therefore the series also converges. Pretty cool. Okay. Okay, let's do one more. So use the integral test again. Again, you should check that it's positive and decreasing. Take my word for it, or check yourself, but I'm not going to check that here. I'm just going to jump straight in and use the integral test. So I'm going to first set up my integral. I'm going from 1 to infinity, and instead of n's, I'm going to put my x's in here so it looks a little bit more familiar. I'm going to do a u substitution again. So I'm going to let u equal x squared plus 1, and therefore du is going to equal 2x dx. Dividing both sides by 2x, I get that dx is du over 2x. So making those substitutions, I have x over u. Dx is the same thing as du over 2x, and these x's are going to cancel, leaving me with a nice integration here. So what I'm going to do is I'm going to first pull out the 1 over 2, and what I'm left with is 1 over u du. Now we know what the antiderivative of 1 over u is. The antiderivative of 1 over x or 1 over u is just the ln of u. So this is going to give us 1/2 ln absolute value of u. And replacing back in u was x squared plus 1. So before we evaluated our limits, let's go ahead and replace that back in. So we have absolute value of x squared plus 1, and we're going from 1 to infinity. So we have 1/2 ln of infinity squared plus 1 minus ln of 1 squared plus 1. Well, we can right off the bat see that this thing is going to be divergent because of this. Infinity squared plus 1 is simply infinity. So this is going to be ln of the absolute value of infinity. And we know that ln of infinity goes to infinity. Therefore, this integral diverges, and so the corresponding series I should put this a little bit more clear. Let's see. Yeah, okay. Diverges also. Okay, so this is a summary of everything that we talked about and everything you'll need to complete your homework. First and foremost, check to see if your series is geometric, if it has a common ratio. If that common ratio is bigger than or equal to 1, it's divergent. If it's less than 1, it's convergent. This is property 1 from theorem 9.2. This is property 2. This is property 3. And this is property 4 from theorem 9.2. And this guy is going to be the integral test. And yeah, so that's a nice little summary of everything that we talked about today.